So I'll begin. So hopefully I should have the solution posted to the mission here before too long, and I hope to grade it and get it back to you guys somewhat quickly. So we'll see. But anyway, dear Father, we thank you for this time we have to meet together and study your creation. Just ask you to guide our steps, help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So today we are studying the theory of dimension. So in particular, I'm going to justify today what's called a basis, right? So like what is a basis? Do you guys remember from like the previous course? Do you talk about basis in there, didn't you? Like a little bit, for sure. Remember, a basis is a set which is what? It's both a spanning set and it does what else? Linearly independent. So it's like two different ways to look at it. The one is it's the biggest linearly independent set you can possibly fit in the space, so it's like a maximal linear independent set, and it's also a minimal spanning set. Like you can't get away with anything less to span the set. So it has both a minimality and a maximality in that regard. And so this section 2.5, which is entitled Theory of Dimensions, is, well, let's just get started here. I'll write lemma 2.5.1 here up on the board. So the big difference between my notes as they currently exist for this course and what they used to be is this section right here. This section is due to my brother. All right, my brother is a mathematician who is more pure than I am. So he has a deep love of foundations, sets, logic, these kinds of things. And you'll see that in this section. Anyway, so here we go. So I'm just saying any errors are here are all his fault. So let S be a linearly independent subset of V. And of course here V is a vector space over F, okay? And let's let little v be an element of V such that V is not an element of S. All right, so you got a point outside your set. Then S union, the set containing V, is linearly independent if and only if V is not an element of the span of S. All right, so this is an if and only if claim, so to prove it, we have to prove the forward and the converse, right? So let's do it. So we'll start with the forward direction. So suppose that S unioned with V is linearly independent. All right? Then V cannot depend linearly on S. Thus, V is not an element of the span of S. So I am relying on that thing I did at the very end of class last time where we showed that there's this other characterization, right? We characterize linear independence by if the linear combination is equal to 0, it forces all the coefficients to be 0, right? But we proved that not being that was tantamount to one of the vectors being able to be expressed as a linear combination of the remaining vectors, right? So in this sense, if this is linearly independent, we can't have V being able to be expressed as a linear combination of the vectors in S, because that would make it not linearly independent. That would make it linearly dependent. And we're assuming it's independent. So that's impossible for V to be in the span. So that's it. That essentially rests on what we proved last time, though, okay? The converse direction. So let's suppose that V is not an element of the span of S. Okay? And we're going to, towards a contradiction, suppose, towards the contradiction, suppose S unioned with the vector V is linearly dependent, right? Then there exist C1, C2, C1 through CK, and also S in the field, not all zero, right? Such that what? Such that C1V1 plus plus CK VK plus S times V equals to 0. I guess I forgot to say where the V1 through VK are. Where are they from?
S.
Right, so like that, let me just put it back here. I'll wedge it, let me wedge it in right here. So my brain skips sometimes. So we'll put it in right here. V1 VK in S, like you said, yeah. All right? So logically, there are two possibilities, right? Either S is equal to 0 or S is not equal to 0. Them's your choices, right? So if S is not equal to 0, then what? Then you can solve for V, right? You can solve for V. V equals what? Like minus 1 over S, C1V1 plus plus CKVK, right? Which is manifestly in the span of S. But what did we suppose at the start of this? V is not in the span of S, right? So this is a clear contradiction to the assumption of the converse direction of the proof. This is a contradiction, right? If S is equal to 0, then what? C1V1 plus plus CKVK rather is equal to 0, right? Where what? What can you tell me about the constants in this context? Not all of C1 through CK are 0. How do I know that? Yeah.
Because you know that of C1 through Cn and S, not all of them are 0, but you know S is 0, so some other one has to be non-0.
You can convert coffee into proof, but not by breathing. Just saying. Exactly that. Since this is 0, and in here somewhere there's something non-zero, it must be by process of elimination that in these first k constants, that's a k, not an n. But you can call it n if you want. That's okay. I'm sorry, that's horrible. I'm an idiot. So anyway, we have this non-trivial, this linear combination is equal to 0, and yet it's not the trivial combination because there exists a non-zero constant. But what did we assume about S? S is a linearly independent subset. So this is also impossible. Thus, contradiction to linear independence of S, right? So what does this mean? If S is equal to 0, we get a contradiction. If S is not equal to 0, we get a contradiction. If S is equal to 0, we got a contradiction. Consequently, it must be the case that it's impossible to find this linear combination with all of these coefficients non-zero such that this happens. What does this mean? There is no linear dependence in this set. Therefore, it is linearly independent, which is what the claim is. All right? I wanted to work through this one with you guys on the board because this is like a reasonable test question. What follows in this section, probably not. But I want to show it to you because, well, there are parts of this section which are reasonable to test. There are other parts which are rather heady. Where's my HDIM? I can't. All right. So, do you guys know what Zorn's lemma is? Anybody?
I think Majeric maybe mentioned it once, but I'd recognize
Which class did he mention it in?
maybe in 221. I think he was probably just.
Really? That's
He
awesome.
didn't actually talk about it. He just said.
But he mentioned Zorn's lemma in 221?
I think so.
Dang, that's hardcore. I don't even do that. Like, and I'm crazy. So, yeah, so we're going to, so what is Zorn's lemma? Zorn's lemma says that if you have a partially ordered set, all right, then any chain in the set which is bounded above has to have a maximal element. So, I'm not going to actually like explain all those words I just used. I'm just going to show you how this plays out in our context. Okay. So, if you'd like to know more about Zorn's lemma, partial ordering, concept of a chain, maximal element, all of these things, and more generally, the thing we're about to use, which is transfinite arithmetic, you should talk to Dr. Sprano. His thesis is in like transfinite induction, so he knows these things somewhat deeply. He also said I shouldn't cover this in here, which of course I promptly ignored. So, all right, so here it is. What I'm trying to prove right now is the following claim. If S is a linearly independent subset of T, where T is a spanning set for V, all right, then there exists some beta that's between the linearly independent set and the spanning set, all right? And that beta is both linearly independent and its spanning set. So let me restate this. This is saying that in a vector space, if you've got two sets, one of which is linearly independent and the other of which spans the whole space, there is a subset between those two which is both linearly independent and spans. In other words, this theorem says that in any vector space, there exists a basis. The reason we need Zorn's lemma is this could be infinite dimensional. All right? So here's the proof. We consider the set which basically is sets which contain S and are contained by the spanning set. So the spanning set T, I couldn't find a reasonable laser today, so I'll have to go with something a little bit more low-tech. So it's the set of all linearly independent sets which are containing S, the given linearly independent set, and they're contained by T, the spanning set. All right? This is a non-empty set. That's the other thing I should have said, a non-empty chain. I forgot that, oh well. It's non-empty because S is in here, right? S is linearly independent, S is a subset of itself, so S is in the set, it's a non-empty set. This is like a script S, let me call it snake. S is in snake, all right? And it's partially ordered by the subset relation. So if we have a chain of elements in snake, that means that if you have two things like S prime and S prime prime in the chain, then one or the other of them is a subset of the other, all right? This is what partial ordering means, in part, is that we either have, so this is kind of like less than, this is kind of like, well, I guess they're both less thans in some sense, but I mean, S prime is a subset of S prime prime or vice versa, all right? So if we consider the union of all the sets that are in our chain, all right, then we can look at that. C is the union of all the sets in our chain. So every set in the chain contains S, all right? Every set in the chain also is contained in T. And if you think about that, if you take a union of sets with these two properties, union behaves exactly like you'd like with respect to containment and subset. Like if you have a union of sets where another set is a subset of every set you're unioning, it is still the case that that set is a subset of the union. If you're taking a union of sets, every which of which is contained in a superset, it is still the case that the union of all those sets is itself taking that set as a superset, right? If you think about this, these would be easy to prove in like Math 200. If we take a union of sets, every which one is contained by a set over here, it's true that the union is also contained by this. If I just say it enough times, you'll believe it. But anyway, I should have made that a homework. Oh well, I lost my chance, right? You're like, well, we didn't have enough homework. You could add more. I'm just kidding. I know. Don't worry. At some point, I'll grade your homework and then scale back. But because your ally in this battle of academics is that I hate grading. So once I start grading, it's very in your favor. I haven't written the rest of your homework. All of a sudden, the number will reduce from like 16 to 14, and then before you know it, we'll be at like 10, or who knows? Maybe like it dropped down to like 6, like in physics. But 2. Let's just do nuns. We'll just have a final. I won't grade anything until the final. How's that sound? Okay, I do have things to cover today. So we've got this set, and everything in the union of all the things in the chain is containing S and in a subset of T, right? And so that means it's potentially an element of snake, right? It's at least it's a subset of T. It's a superset of S, right? The union of the chain is in there. But in order to actually be in S, we need what? We also need that it's linearly independent, I suppose. In any event, every set in C contains S and all right, I just said that. I'm sorry. I'll get to it here. So suppose we have V1 through VL in the union of the chains, such that we have a linear combination equal to 0. Then for each I, we have VI as an SI for some set in the chain, and without loss of generality, we can relabel them so that they're nested 1 inside 2 inside L, right? Just if they're not already that way, just relabel them so that they're like that. And if that's the case, how does subset work? If the element's in here, it's in here, it's in here. Like everything in this nested inclusion is in this guy, right? Which means that all of these are in SL, but SL is by construction a linearly independent set. Consequently, the coefficients must be 0. Thus, C is linearly independent. Therefore, C is in the snake. All right? So what all of this shows is that the snake is a non-empty set such that every chain is bounded above, in particular by the union. It's bounded above by that union of all the chain members. Thus, Zorn's lemma applies and provides that snake must contain a possibly non-unique but maximal element. We call such an element beta. Then we have that beta contains S, it's contained in T, and it's linearly independent. So all that remains is to prove that beta spans V. Then we'll have that it's a basis. Although if you're paying close attention, I haven't actually defined basis yet in the notes. All right. So suppose T is not contained in the span of beta. All right. That would mean that there's some V in T such that V is not in the span of beta. But then by our lemma over there, that would mean that beta prime formed by beta union V is what? If you take a vector outside of the span of a linearly independent set and you union it with a vector, you get a linearly independent set, right? So this beta prime would be linearly independent. But it's what? It's a linearly independent set that's containing beta. And that means beta prime is in snake. So that's impossible because beta was chosen to be maximal. It's the superset of everything. So you can't have something. In other words, another way to read this would be, okay, so then beta has to be equal to beta prime, you know. But well, no, I can't say that because there can't be equality here because we've assumed that V is not in the span of beta, and if these were equal, then V would be, anyway, V would be in the span of beta prime. But we can't have that because it's maximal. Therefore, there does not exist a V in T that's outside the span, which is going to force equality. Therefore, we must conclude that T is a subset of the span of beta, and consequently V is equal to the span of T, which is a subset of the span of beta, which is a subset of V because this is a linear combination of vectors in V, which is necessarily a subset of V because V is a vector space. And what happens if you've got, span of beta is a subset of V, but also, well, anyway, I've lost my train of thought here. The point is that the span of beta is equal to V, thus B is our desired linearly independent spanning set. As such, since we can do this for any vector space whatsoever, this brings us to define a basis. A basis is a set in a vector space that's linearly independent and spans the set. It spans the space. All right. Yeah. So I wouldn't expect you to replicate that on a test. Like, that wouldn't be friendly. This, on the other hand, meaningfully interacts with the definitions I expect you to know and work with, okay? So the lemma is a reasonable test question, but that proof that, meaningfully interacts with Zorn's lemma is probably a little bit much. Now, I might ask you a simple trivia question about it, but that would be about as far as it went. Now, so here's another corollary. A basis can be created by an extension of a linearly independent set or a reduction of a spanning set. All right, in other words, every linearly independent set can be extended to a basis, and every spanning set can be reduced to a basis by removing vectors. So we simply use the theorem above. We take S as the empty set, which is a subset of any vector space, and we take T equal to the vector space itself. A vector space is always a spanning set for the vector space because every, we prove that, like, S is a subset of span S, remember? So the span of V contains V. I mean, it's kind of silly, but so using the previous theorem with S equal to the empty set and T equals to V, that means there has to be at least one basis by the previous theorem. And if S is linearly independent, we can simply let T equals to V. We get S is contained in some basis, right? And if T is a spanning set, we let S equal to the empty set, and we get basis beta that's contained in T. All right. So in other words, I mean, it's a corollary. It's essentially just apply the previous theorem to any set. You can either, if it's not already a spanning set, you can adjoin things in it to make it a spanning set. If it's not already linearly independent, you can remove things from it to make it linearly independent, right? This one's a little bit more technical. This is the exchange lemma. It says that if you have a linearly independent set of vectors and, and suppose T spans V. I guess T is another set. That's fine, T is another set. And T spans V. Then there exists some partition of T, say W1 through WL. And this right here is a funny thing. This is the disjoint union, all right? Disjoint union with T prime. So T is a disjoint union of these vectors and T prime. Then if we take T prime prime as this set of vectors unioned with T prime, that still spans V. In other words, if we select the right, it's almost better just to look at the last sentence with these ones sometimes. In other words, if we select the right WIs, we can swap out W1 through WL, and alpha will still span our vector space. Right. So, like, in other words, you've got to, so let me kind of put this in different words. You've got T as a spanning set, all right? you've got this set of linearly independent vectors. What this theorem says is that you can get rid of part of T and replace it with alpha and still get a spanning set. So I will not go through the proof because we don't have time to go through all of these. But I do think the proof is understandable. I've gone through it a few times. The next corollary, if alpha is a finite linearly independent set and T is a spanning set, this notation is cardinality, so like the size of alpha is less than or equal to the size of T. So I don't know if you guys do this in Math 200 or not. Do you talk about like inequalities with cardinality? Like the cardinality of the natural numbers is less than the cardinality of the real numbers? Just a little bit. What that means is that ultimately this means that like alpha could be a subset of T, but not the other way around. They could be equal, but for two sets to have the same cardinality, it means there's a one-to-one mapping between the two. That much I'm sure you covered, right? Anyway, getting back to the point here. Moreover, if V is spanned by a finite set, it cannot have an infinite linearly independent subset. So the proof is by the exchange lemma. Since you can replace elements of T with elements of alpha, T must have at least as many elements as alpha. So if you had a finite spanning set and you could somehow replace it with an infinite list of linearly independent vectors, well, that's crazy. You can't take a finite set and replace the elements of it with an infinite set. Like, can you put an infinite number of marbles if you've got 100 places for marbles? Like, it's not possible. So there's that. So you can't have an infinite set inside. If you have a, I'm not sure if I said it right. Alpha is a finite linearly independent set. T is a spanning set. So the cardinality of alpha has to be less than the cardinality of T. And if V is spanned by a finite set, it cannot have an infinite linearly independent subset. Here's another one. If any basis of a vector space is finite, all bases of that space are finite. All right. Moreover, any two finite bases must have the same size. So what our previous corollary states is we cannot have a finite basis and an infinite basis. Otherwise, it would come to an absurdity by the exchange lemma. All right? So now we suppose we must have finite bases then. If there exists a finite basis, any other basis must also be finite, right? So suppose you have alpha and beta, two finite bases. Then since alpha is finite and linearly independent and beta is a spanning set, the previous corollary says that the cardinality of alpha has to be less than or equal to the cardinality of beta, which here just literally means the number of elements in the set, because for a finite set, cardinality is just the number, right? But by the same token, beta is a finite linearly independent set and alpha is a spanning set. So by the previous corollary, we have that the cardinality of beta is less than alpha. But that forces the cardinality of alpha to equal the cardinality of beta, which says that any two bases of a finite dimensional vector space must have the same number of elements. Next up is a deeper theorem. Any two bases of a vector space must have the same cardinality. I'm not saying just finite dimensional. All right? So I'm saying that, like, we could look at the set of polynomials. All right? A basis for the set of polynomials are the monomials. Things like 1, x, x squared, x cubed, x to the fourth, and so on, right? What's the cardinality of that? Well, it's indexed by the integers, right? So the cardinality is, it's countably infinite, right? Its size is aleph naught, if you like. So what this says is if you had any other basis for the vector space of polynomials, it must also be a countable basis. You must also have a way to index it using counting numbers, using natural numbers. You couldn't have a basis for the set of polynomials which was the size of the continuum, that was like the size of the real numbers. If one basis is countable, they're all countable. Countably infinite, I'm saying. So if you have two bases for the vector space, beta and beta prime, we already know that either are both infinite or both finite. If they're both finite, the previous corollary establishes that their cardinality is equal, right? And most often this is our context, okay? So what's left? Well, suppose that we have an infinite basis, and for the sake of contradiction, that the cardinality of beta is less than the cardinality of beta prime, right? And then he gives an argument here. He says V is in beta, beta prime spans V, so there must exist vectors in beta prime and constants in the field such that a linear combination produces V, right? And then he just defines this F sub V to be this set here, and so V is going to be a subset of that span. But then he builds alpha here as the union of these kind of things, all right? Then alpha is a subset of beta prime, and for each V in beta, we have V is in the span of F sub V, which is in the span of the union of all the F sub V's. So beta is a subset of span alpha, and since beta spans V, we have V is equal to span beta is equal to span alpha. But this is problematic. Since what? Since alpha is a union of finite subsets indexed by beta, and we had the cardinality of alpha is less than or equal to beta times aleph naught. So if you have an infinite cardinal and you multiply it by countable infinity, you get back the same infinite cardinal. This is the part I said you need to go ask Dr. Sprano about. All right, so then that means that this is true. Therefore, alpha must be a proper subset of beta prime. And so there's some W that in beta prime which does not belong to alpha. And then we can take alpha disjoint union with the set with the W that's independent, and W is not an element of the span of alpha, but this means that the span of alpha is not equal to V, which is a contradiction. Therefore, we must have the cardinality of the two. I don't follow this proof entirely because I'm not like super well versed in transfinite arithmetic, honestly. But I do think it is a complete and logical proof that explains why the basis of a vector space has to have the same cardinality. What I'm trying to say is it's not a question of understanding. Like if we had an hour to just sit and mull over this, we'd all get it, all right? But we just don't have that kind of time. I just want to point out to you that it is something that's true. Two vector spaces, two bases for a given vector space have to have the same cardinality. All right? And that means that we can define the cardinality of the basis to mean something. What is it? Well, it is dimension. Let V have a basis beta. The dimension of V is the cardinality of the basis. So like in homework 2, mission 2 for you guys, I've got a problem where I have you find the solution set over Z is 17, and I ask a couple different questions. Like one is what's the size of the solution set or the cardinality of it versus what's the dimension of the solution set? Because the solution set is a subspace, which is a vector space, which means you can find a basis for it, right? Which vector spaces can't we find a basis for? The answer is none in principle. In practice, though many. Let me not be so, I'm trying not to mock the students so much. I've been chastised for this, but I feel your pain. But logically, any vector space we can find a basis for, right? How do you actually do that for examples? I'd like to actually get into that today. Let me get on with it here. So the dimension of the vector space is the cardinality of the basis. Let's see some more theorems. If V is a vector space of finite dimension, and you have a subset with n vectors in it, then beta is linearly independent if and only if beta spans V. In the finite dimensional context, linear independence of n vectors is equivalent to the spanning of n vectors. So if we're in the context, if we already know we're in an n-dimensional context, it suffices to either check spanning or independence to prove basis. But this only works in finite dimensions. And in the infinite dimensional context, you can have a spanning set, right, which has infinitely many things in it, and yet it's not linearly independent, and vice versa. You can have an infinite linearly independent set which doesn't span in the infinite dimensional context. One of your homeworks in Mission 2 illustrates this, like I think maybe the last one. The shift operators are good examples of this. I mean, here's an example. One, like the even monomials, that's a countably infinite linearly independent subset. So the cardinality of this set is aleph naught. All right? The dimension of the polynomials is aleph naught. So this has the same cardinality as the dimension of the polynomials, and yet it's linearly independent, and this does not span because you don't get the odd powers. On the other hand, this guy, if you do 2 and then 1 and then all your, just basically tack 2 onto the set of monomials, this is a spanning set. Its cardinality is also aleph naught, yet it is not linearly independent. So you see linear independence and spanning, that theorem doesn't hold for the infinite like it does for the finite. In the finite, if you got n vectors, if you got as many vectors as the cardinality of the basis for your space, if we have it spanning, we also have it linearly independent. There's something really cool that happens in finite dimensions that's just not happening in infinite dimensions. All right, so full disclosure, I have proved these things in past semesters just for finite sets, for the finite dimensional context. If I do that in here, it takes about 2 lectures of gory induction proofs. And we get through it, and we don't, I don't know, like, you should, this right here, I think is good. This you should understand. If you really understand this proof, you understand 80% of what I'm trying to get at in this section, all right? So my larger point to you is just for, like, this is just context. We know there's a basis, we can find it. Now the question is, how do we find it? Like in practice, how do you actually find bases, right? So let's work an example. Let's suppose we've got ourselves W, which is, oh, I don't know, A in, let's say, R3 by 3, such that A transpose equals to A, and the trace of A is equal to 0. Let's see if we can find a basis for this vector space. It's a subspace, right? So by the way, guys, as you're reading my notes, if logically you're thinking through things and you're like, you know, there's something missing here. I really want this theorem or something that's missing from the notes. I feel like logically it should go here. Email me about this. I can improve my notes from your comments, you know? I have spent a lot of time this summer thinking about your notes, more than any other course, guys. Like, you're my top priority by far. Don't tell the other classes. But I've already spent several thousand hours thinking about complex, so that one's kind of okay. They're not neglected, it's just I have a wealth of things already done. But here, this is a rewrite of the course, right? So something will get missed in the mix, right? So the problem here is find a basis for this. We're going to prove it's a subspace along the way, all right? So you guys tell me at which point we've proved it's a subspace. So here's how I do these. I write A is equal to A, B, C, D, E, F, G, H, I. Because I don't like subscripts. Yeah. What's the condition? This is equal to A transpose, right? Which would be A, B, C, D, E, F, G, H, I. Those are equal. What does that tell me? A equals A, E equals E, I equals I. True, but useless, right? True, but useless. What's more exciting is we have what? B equals D, C equals G, right? And F equals H. I've got those from equating above the diagonal, right, guys? Like this and that, this and that, this and that, right? What happens when you look below the diagonal?
You got the same thing.
The same thing again, right? So apparently that's all we get, those three equations. So we have now taken full account of A transpose equals to A. That's what it does for us, right? How about the traceless condition? Trace of A is what? It is A plus E plus I equals to 0. I haven't proved it, but it's actually somewhat obvious that these four equations we found are independent. So what's the dimension of the space we're looking at? Our backdrop is, you say 4-dimensional, almost right. Our backdrop is 9-dimensional. 3x3 matrices have 9 dimensions over the reals. We have 4 independent conditions. We should expect a 5-dimensional space. W is 5-dimensional. So we're looking for a basis that has 5 things in it. All right, so let me suggest that we use, let's choose our parameters. What do you guys want to keep? I like A. We'll keep A. And we'll keep, maybe I can't keep A. I guess I'll keep B, C, and F maybe. And I'll keep E too. So if if it's a 5-dimensional space, I'm going to need 5 parameters to describe the space. So, all right, so let me show you how this goes. So A, I should have made a smaller example. I'm an idiot. Anyway, so A equals to minus E minus I, right? Except I don't want to do that because I'm keeping A. So you keep the parameters, right? So that's not what I should do. What should I do? What's the point of this?
I equals minus E minus A.
Thank you. Minus A minus E, right. Great. So A is A, and then E is E, and then I is minus A minus E. All right. I'm going to put some dividers in so that we can see what we're doing better. All right. So that's what goes in the diagonal. And then I said we're keeping what? B, C, and F as parameters. So I'll put those here. B, C, F. Okay. And I put them over here as well. B, C, F. This, my friends, is the form of an arbitrary matrix in the set W. And once I figure that out, once I apply the conditions to the object, then it's a simple matter to write down the basis. See, because this is equal to A times 1, 0, 0, 0, 0, 0, 0, 0, 0 plus E times 0, 0, 0, 0, 1, 0, 0, 0, minus 1.
You forgot the minus 1 in the first.
Oh, yeah, I would have, thank you. I would have, eventually would have caught up to me. And then I got my A, I got my E, and then I got my B. 0, 1, 0, 1, 0, 0, 0, 0, 0. If only there was an easier way to write these things. Plus C times 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0. And then my F times 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, I think, like so. Let me suggest that these are like not the right notation to use. Like we could save ourselves like a lot of writing if we embraced using the notation which I've shared with you guys, which is that this is E11 minus E33, and this right here is E22 minus E33, and this right here is E12 plus E21, and this right here is E13 plus E31, and this right here is E23 plus E32. And if you like, I can put a curly bracket here and add some commas. And call this beta. And the point is that W is equal to the span of beta. The dimension of W is 5. This is a 5-dimensional vector space. We've proved it's a vector space when? Alexa, when did we prove this is a vector space? I used the voice. You have to acknowledge it. All right, she's not acknowledging it. So what? It's a span, right? Yeah. And how did I show it was a span? Well, algebra, right? Logically, do we know this is a 5-dimensional vector space? Only through my sort of hand-wavy degree of freedom arguments, right? So how do we prove it's a 5-dimensional vector space? We've got what's on the board proves it's a spanning set. Is it linearly independent? If you take a linear combination like this one and set it equal to 0, the 0 matrix, does that force A, B, E, C, and F all to be 0? Quite clearly it does. This calculation shows that it's both a spanning set and linearly independent if you think about it for a second. Therefore, it is 5-dimensional. Honest to goodness, 5-dimensional, right? Example 2. We'll do something like way easier. Suppose your W is equal to polynomials, we'll say in T, such that f prime prime of T is equal to 0. So, you know, if we have f prime prime of T equals to 0 and it's a polynomial, what's that tell us? That tells us that f prime of T is equal to a constant, right? What did I do? I integrated. So again, integrate again. We get f of t is equal to what? Ct? Let me call this C1. C1t plus C2. Therefore, W is equal to the span of, apparently, t and 1. Are those linearly independent? You can prove that t and 1 are linearly independent. How would you prove that? So the dimension of W is what? Apparently 2, right? We could go back to that theorem we proved last time. How can I prove that t and 1 are linearly independent? suppose otherwise, right? If we had t is equal to k times 1, then that would say t is equal to a constant, right? But that's absurd. So therefore, t and 1 linearly independent. If you don't like that, you could of course take c1t plus c2 equals to 0, and you could plug in t equal to 0. What does that give you? c2 equal to 0, right? And then you've got c1 times t equals to 0 left. Set t equals to 1, and you get c1 is equal to 0, right? This equation is a function equation, so this holds for all t in the reals if you want to think about polynomials as functions, right? I have much more discussion of this in the notes, yeah? But I thought I should work at least 2 examples, so forgive me for not spending more time on the the proofy part today. I wanted to at least make some time for a couple of examples. Next time we'll talk about what is a coordinate map. And then, so in fact the basis is not just a linearly independent spanning set. We insist that it's ordered, right? So we're going to make a distinction between which one we put first and which one we put last, and that is going to, removing that ambiguity of the ordering will then give us specificity and indeed a unique meaning to coordinates with respect to a basis. So that's where we're going next time.